Hi there. Thank you so much for having me today. I'm here to present in front of you our conception, analysis, and design of the artificial blood vessel. My name is Stephen Alport, and as previously discussed, I was tasked with finding a suitable material for designing an artificial blood vessel. And so just here you can see a little task list of what I went through and processed in terms of our milestones for how we would conceive this and go about the entire process. Just to keep the small and minimalized stuff short, I just wanted to go over the reason for having this is just for replacing arteries that have gone awry, and they are chosen and selected for the need of the patient, implanted through surgery, and it's truly the location of the artery that determines the best material for the job. As done in our simulation, we chose the radial artery, which is located in the arm, in the forearm area between the elbow and the wrist. And as seen here, these are the three materials that are used most frequently in the industry for replacing arteries. The first one is polytetrafluoroethylene, the second being Dacron, and the third being polyurethane. Dacron has been used the longest out of the three, although all three are often found to be suitable materials and viable options as they've been around for 30 plus years for each of them. According to our simulations, we did collect in majority data about the pressure and how it affects the blood vessels in their tube shape. We did run three simulations, one being at a 1 millimeter length, a second one being at 10 millimeter length, and a third one being at a 100 millimeter length for the blood vessels. Right here is shown the 100 millimeter simulation. And this one has been chosen as it is seen as the best representation possible of what a real life example would be like. Considering that the radial artery does span from that wrist area to the elbow, that is well over 1 and 10 millimeters. It is a bit longer than the 100 millimeter mark, as that is only 10 centimeters, but it draws the closest resemblance. And so that's why we're taking a look at it rather than the other two simulations today. I've outlined the most important detail out of this entire simulation being that the max pressure observed in this entire tube when the blood was flowed through it is at 23.4 kilopascals. Now, our simulations were run using gathered data on what the average blood flow is, which is about 0.406 cubic centimeters per second, or under extreme circumstances up to 2.03 cubic centimeters per second. And these were run against the average blood pressure in the radial artery, which is around 149 millimeters mercury, or in a more reasonable unit is 19,865 pascals. Now, the reason for the max pressure being the most important detail for us to be observing is that all the materials that we're going to look at are characterized by one very crucial thing, especially being in the body, and that's going to be their yield stress, or the point at which they're going to break down and start to deteriorate or deform based on pressure alone rather than time and that sense of longevity. And so it is one of the more crucial aspects in how we have determined our final material, being that a pressure too high in the blood vessel will easily rupture a material that's not strong enough. Now, in short, with all those observations of what we have with polytetrafluoroethylene, Dacron, and polyurethane, these are the simplistic results for how we're going to get an economic decision, being that, as you can see, the yield strength is ranked or rated for each one in line. PTFE at 862 kilopascals, Dacron at 24.1 megapascals, and polyurethane at 12 megapascals, showing that Dacron does have the greatest yield strength, with polyurethane being second, and the PTFE at third with 862 kilopascals. Now, you'll notice that all three of these numbers in their yield strength are far, far above the maximum expected pressure in our radial arteries, as those were only up to 23.1 kilopascals. Therefore, all three of these materials that have been found and used in industry are suitable for a radial artery, artificial artery implant. Therefore, the next line of reasoning is going to be our cost and how we would analyze that. Now, that's going to be in the next column to our right, with a slightly different order, being that PTFE is going to be the most expensive, with Dacron being the second most expensive, and polyurethane being the least expensive. It is through this analysis that we decided that polyurethane will be our best option for constructing a artificial radial artery. Although if we were in the industry or into looking for other possible solutions, all three of these materials are capable of being implanted into a human being for that artificial artery, but will not be as cost effective as simply going with the polyurethane. That's all I've come to you today to present. If you have any questions, I'll be here afterwards. Thank you so much for letting me present in front of you today. Thank you.